And if you ask good questions, we have 3 books thanks to O'Reilly and Pragmatic Programmers that we can give away, but we don't have any Prods books in this.
So your best chance at a good question is just to be one of the first 3 questions, I think. So my name's Jehiah. I work at Bitly. I am the lead engineer there, and I've been there for about 1.5 years now, which in startup years is about 27, I think. So what do we do at Bitly? We take big things and we make them little. If you didn't catch the connection to the puffer fish, now you have. So we take links that look like this and we make them look like this, which of course makes them convenient to use on Twitter, Facebook, email, any place else you want to share a link with a friend, and you don't want to have them kind of retype 1,000 characters or even have to care that it's 1,000 character long link. And one of the interesting things that everyone says when they start working at Bitly is they're confused as to why we call them URLs. Because we deal with them all day long, it's a real pain to call them URLs. So they're URLs, in case you were wondering. So what do? We give you, when you're sharing links, we give you statistics about who is clicking on your links, both on the kind of aggregate level. So this is one of my test accounts here. We give you statistics on the aggregate level as to how many people are clicking through on the links that you're sharing and where they came from and where they're going to and what location they're in. And we give you all that same kind of information in real time for each individual link. So you can see as that link is shared, all of the traffic on that link and where they came from and where they're going to. And you can get to the information page for any Bitly link that you see just by adding a little plus sign at the end, and it'll take you to a page that looks like this. So all that to say, we have a lot of data at Bitly. We have a very interesting section of things that are happening on the social web because we're not just an application that's building on top of the Twitter ecosystem. People are using Bitly links across a lot of different platforms, which means we get to see things very quickly when something like the tsunami happens in Japan. We see the links people are sharing about that and the content of those links very quickly. The half-life of a link, as we call it, is almost 30 minutes. So what that means is the traffic that will happen on a given link, half of it has happened within the first 30 minutes of when that link is shared. And so there's a lot of other interesting things we can learn from the Bitly data set. One thing that I was kind of curious about is what is the actual usage of Bitly links between iPhones and iPads, and how does that change throughout the day? So this is a chart of people in New York City that are clicking on Bitly links either via their iPhone or their iPad. And you see these 2 charts are fairly different. You can tell from both of them, though, when people sleep, which is to say not much at all. Apparently people in New York only get 4 or 5 hours of sleep, which probably is pretty accurate sometimes. But iPhone users are kind of steady throughout the whole day. Apparently a lot of people have boring jobs and they're just on their phones. Or maybe they work in some place where they don't have internet access, and so they're just reading Twitter or whatever else on their phone. But iPad usage is fairly different because it's everyone using it when they get home, when they're sitting on their couch or in bed reading, catching up on the news. So you can kind of see a lot of information that you wouldn't readily know that you can tell through the Bitly data set, which is how different tablet computing is from handheld phone computing, which we can tell just by the nature of what people are doing with Bitly links.
I'm sure there's more than 90 more iPhones than iPads.
Yes, there are. So this is not normalized. This is actual counts. Yeah, if they were normalized, it would look a little different, but you'd see the skew more between the 2. And of course, I picked just iPhone just because there's a lot of them, but I could have easily done this for other mobile phones too. So it brings me to what I call the big data problem. There's a lot of talk about huge data sets out there, and it's difficult to know what that really means. So I'm going to define this for the set of what I'm talking about, and that is that there's kind of anytime you have a data set that's larger than what fits in RAM, it becomes difficult to work with that data set. And especially when you have a lot of updates right there in the middle. It's really easy if you have a huge data set, but it just sits on the disks and nobody ever, you're not adding any data to it. There's no updates to it. It's really easy to manage a big data set. And the same way, if you have a small data set and you have a lot of updates, it's still really easy to manage because it can fit in RAM. MySQL can do, wonders if your data set's like a gigabyte or something, right? Really easy. But when you start combining those two, you have a lot of challenges that you have to address. So I'm going to talk today about 3 open source pieces of code that we've written in C that kind of help us address these problems. And the first one that I'm going to talk about is a way to kind of break this big data set and a lot of updates into 2 separate pieces where you have a big data set that has no updates, which is read-only, and a smaller data set that has lots of updates, because both of those are easily solvable, but together they're not. So if we think about what is the easiest kind of read-only data format, everyone thinks of CSV. CSV files are really, really easy to manage. Every database will export into CSV. You can find a million tools that can deal with it. So what we've done is we've created an application, a database called SortDB. SortDB is built on top of libevent. So if anybody is familiar with Memcache is also built on libevent, so it's super fast. And all you do is you point it at a CSV file that's been sorted. So the first key in that file is in sorted order, and you can make that CSV file HTTP accessible and get, do queries on it by keys in that first column, or do range queries on prefixes, or do multi-get queries. And it just returns you those raw records, which is really convenient because if you can structure your data set so that it's read-only, using something like SortDB scales very easily because you can just break your data set into smaller chunks and put it on separate machines. You could start up multiple copies of this pointing at the same database, the same CSV file, and it's really fast. We actually had trouble kind of benchmarking what the upper limits of this are, because what it does internally is it takes that CSV file and it memory maps it so that the first access is reading from the disk, but the second access is reading from memory, which memory is really, really fast. So we easily get 10,000 requests a second across this database. And the link down there at the bottom is a link to the GitHub repository, which is where we have this. So SortDB is one tool that we use to kind of split our data set into a piece that's kind of read-only and very easy to manage and very easy operationally to kind of scale out, and then split it into a smaller data set, which we would also kind of use a more traditional database that can handle updates. So if you can split your data apart, anything that is time-bounded, you don't never update the records that are from last week or last month, or a lot of data sets are kind of write once, and then that record lives statically forever. So tools like this help make those problems solvable. Another tool that we've built that we use heavily is SimpleQ. There's been a lot of interest in a lot of queuing technologies, and they've really matured a lot in the past year or two. If you're interested in the more enterprise kind of class queuing system, I'd highly recommend you look at ZeroMQ. But one of the things that we've done is we've built an in-memory simple queue, which is based on libevent again, so it's really quick, and we'll run one of these on each of our machines, and they're really easy to use and access from other applications. So we do a lot of Python code, and it's really easy to make HTTP requests in Python code. So we like backend systems that expose HTTP interfaces. And HTTP interfaces are really easy to scale. It's really easy to find a hardware load balancer for HTTP requests. You're not going to find one for MySQL requests the same kind of way. So this is just an example of how we use it, just to put data in and get that same data back. It's just a first in, first out queue. So kind of how do we use that in our architecture? Anytime we need to write something into our database, instead of writing directly into the database, we try to decouple the two pieces. The first piece being receiving that data, and the second piece being writing that data into the database. So what we do is on the receiving side from the website, that website will push that data into the simple queue. And then we'll have a reader, which in our case is just a really simple Python script, that will pull that information off and that'll write it into the database. And what this gives you is it gives you a separate spot from where you're receiving data to scale out matching up with your backend. So as your backend grows or moves, or as you start splitting that data to go into multiple backends, you have a very simple queue reader which can do that for you. So here's kind of a drawing of how that reader step can scale separate from receiving the data. And typically, we'll run everything on the left-hand side of this chart on one machine. And then the right-hand side where you see the dotted lines is where it would connect out to remote machines. And there's a lot of important flexibilities that this gives us in approaching data problems, because you want to be able to, as your databases grow and evolve, you need a way to kind of hook in new databases. You need a way to hook in new, to try out new things in parallel without kind of disrupting what you're doing already. And this kind of queue reader spot that is a code layer that sits in between receiving and writing the data out is a good spot to kind of experiment with things. Maybe you want to try 2 database systems in parallel. It's a good spot to do that without really disrupting other things. It becomes very simple code. Operationally, in our queue readers, we use something that we call a back-off timer, which when you write your code so that all the logic or all the accesses to the database to put information in it happen in this kind of stage after the initial request from the client has been received and returned, what you can do is you can just build some retry conditions and build some kind of niceties operationally. So we use this little back-off timer. And what this does is it just kind of keeps track of successes and failures in writing to a backend, which would be on some other machine. And whenever it starts seeing failures, it'll just keep track of an interval that is how long it should wait between requests. So what happens is, if you have your database that, say you have intermittent connectivity all of a sudden, or some sort of networking blip on your database, or it just crashes or something, all of the things that are writing into that database will start seeing problems and they'll slow down their rate, which makes it very easy for things to recover on their own, because anyone who's done databases knows that the worst thing is when you have a machine that it might be fine under just a little bit lower load, you'd be able to handle maybe 80% of everything, but when everything is trying to connect, it just falls over and you get nothing done. So things that can kind of slow down their processing rate or kind of pause a little bit without impacting everything else, kind of a little bit of a buffer between the processing speed of one system and another, is really convenient to have. And so when we plug that into our script that pulls things off of the queue and writes it into the database, it looks like this. It's just our queue readers are just loops that are making GET requests to the queue, and they'll pull a block of data off that they need to process. And as it does its handling, if it's successful, it'll just keep track of that success. And if it fails in any way, could be, unknown failures are the worst, but you can handle unknown failures and just slow down.